Let's go ahead and take a look at week 11, the topic of transformations, example number 2. In this example, we've been given a quadratic function, h of x equals x squared plus 6x plus 8. And what we're interested in doing is shifting this quadratic around to a few new places in the plane. First, we'd like to shift it down 7, give its equation in standard form. Then, separately, we will shift it left 2, and again, give its equation in standard form. If we're going to shift any function down 7 units, regardless of I know its expression or not, then we know that we can use the function notation representation of h of x minus 7. I know in this case that shifting down is a vertical shift. Vertical shifts affect our y values. Y values are outputs, and so I know that my adjustment should be outside the parentheses. Further, what I know is that I can trust that all of my vertical adjustments that I make perfectly match my intuition. Down 7 suggests minus 7. That agrees with my intuition. Now what I'd really like to do is write this actually as a quadratic based on h of x. The good news for me is I know what h of x is. It's x squared plus 6x plus 8. So I can make the substitution x squared plus 6x plus 8. And again, we're shifting this down 7 units. So just with a little bit of simplifying right here, we can write this as x squared plus 6x plus 1. As a little bit of justification to my answer here, I can see that our original graph for h of x had a y-intercept of 8. We shifted it down, so the y-intercept at 8 is now instead located at the y value of 1. In general, our vertical transformations are always going to be, in my opinion, a little bit easier than our horizontal transformations. There's 2 different reasons why, and we'll see both of those crop up over here. In our second example now, rather than shifting this down 7, we are instead going to shift left by 2. What I know is that shifts left is a horizontal shift. I know that horizontal shifts move my x values. I know that x values are inputs, and therefore the adjustment that we're making is going to be inside the parentheses. I also know the slightly tougher thing over here than in our example A is that my horizontal adjustments are always the opposite of my intuition. So typically when I would think left 2, I would think negatives, but since the horizontal transformations that we make are always opposite of our intuition here, we'll see this is going to be an x plus 2. I like to think of this as a compensation thing. When we're trying to evaluate h at some location using h of x plus 2, since 2 is going to be added to my contribution before h is applied, I can get away with giving 2 fewer x if I want to get the same output as before. 2 fewer x is the same as left by 2. That's the 2 fewer that we can get away with putting in and still achieve the same outputs as we were getting from our original h of x function. What's important here, that's also a little bit more difficult than the A setting over here, is that subtracting 7 off the end was super easy. We just had to do 8 minus 7. Over here, we got to be a little bit more careful. Remember that function notation represents the idea of a placeholder. X is just holding our place in line until we come in with the value that we actually care to evaluate h at here. So rather than just squaring x, I'll now need to square x plus 2. Some things like this here. So what we can see here is where there once was x, there now is x plus 2. So everywhere in my quadratic expression that I see x, I should instead have a x plus 2. So rather than squaring just x, we are now going to square x plus 2. Rather than just multiplying 6 by x, we're now going to multiply 6 by x plus 2. I'm noticing that the 8 has nothing to do with x, so it's not going to get adjusted at all. What we'd really like to do is write this in standard form. This is a pretty terrible format for a quadratic right here. It's really hard for me to read off any good information from this, so I'm going to go ahead and expand this. Remember that when we square a binomial, we do not just square the 2 terms. This is not just x squared plus 4. We need to remember that there is always this cross product term. If you would like to help justify this to yourself, you should write out x plus 2 times x plus 2, and you should FOIL those guys out right there. What we should be getting when we square x plus 2 is x squared plus 4x plus 4. When I multiply out 6 times x plus 2, I'll get a 6x plus 12. And finally, plus 8 on the end. We can go ahead and collect some like terms and we'll be done. We have a single x squared term. 4x and 6x is going to give me 10x. 4 plus 12 is 16. 16 plus 8 is 24. So it seems like our final answer here is x squared plus 10x plus 24. I just like to real quick help justify this answer a little bit because it's really hard to see this visual shift algebraically. It's not at all directly obvious to me visually that these two are off only by a shift by 2 from one another. So what I'm going to do to kind of help visualize this is look at where their roots are located. Hopefully you can see pretty easily the factored form of this is x plus 2, x plus 4. Therefore, our roots of the original equation are x equals negative 2 and negative 4. If we do the same thing down here, when we factor this, we should find the factored form to be x plus 4, x plus 6. And when we look for our roots, we should find them to be located at x equals negative 4, negative 6. What I can see is that relative to our original, our root at negative 2 was shifted left by 2 units and so is now at negative 4. Our root at negative 4 has been shifted left by 2 units and is now at negative 6. So I feel really good about this standard form quadratic that we've come up with. Even though I can't see the shift left by 2 anymore between the two standard forms, my roots really help convince me that this is going to be the case here.